thank you very much, those of you who invited me. I'm going to talk about 30 plus years of modeling communicating systems. So, it is not this kind of modeling. But you could actually say, why am I here at all? Because this is Lambda Days. Well, the reason is, well, first of all, I was asked, but second, I hope I have something to say which is of interest, because nearly all the modeling I do is in a functional style. And many of the tools that sit behind some of the systems and models that I've been talking about have been written in functional languages. I was originally a term rewriter, and I think still in my heart I am a term rewriter. So indeed there's a lot of term rewriting sitting behind all of this. So I hope that tells you why the relevance, and also that perhaps it's just a nice way to end the day, so it's something a wee bit different. Now, I'm going to go very fast, this is almost going to be a talk, except for the first slide, by cartoon, but please be assured there's some real science behind everything I say, and you can question me with those difficult questions at the end. Anyway, so what have I been doing for most of my academic career is looking at applications-driven foundational research. So it's about models and formalisms. And what I'm going to do in this talk is I'm going to go through 5 examples. So that's about 8 minutes per example. I'm going to tell you what's the question, what are the techniques, and then I think the key thing that I want to get across for each of these is what did I learn through each of them. And then at the end, I'll just conclude with, recurring themes in the future, as you always do. Okay, so here's the examples. The first is protocol languages. The second is signaling and biochemical networks. The third is domestic network management. The fourth is a mixed reality system. And the final one is user interaction styles. And I chose these because they reflect some of my own evolution over the years in the kinds of systems I got interested in and the difference in tools, etc. So as I said down there, the applications have changed over time, and so have I. Hopefully for the good. Okay, so starting off, protocol languages. This is work that started in the late 80s, early 90s, and it's about ASN1 and ACT1. These are both protocol languages. They still exist. And this was work sponsored by BT. And there's an ASN1 user in the audience, at least one. Great. So these are 2 ISO languages. And the question was, what is the relationship or the translation between the two? Because BT wanted to translate some of their protocols from ASN1 basically into LOTOS using ACT1. So why, again, to integrate protocols to and in both the languages? So I developed a denotational semantics for ASN1 into ACT1. Now, I will spare you the details of this denotational semantics, but just to give you a wee flavor of it, for example, 3 functions, evaluations for values, tval for types, mval for modules, and then there's the usual definition. So I want to point at this. This is no good. Anyway, so tval has a type, and then here's an example. Tval of a sequence of integers. Remember those in ASN1. Gives you this block of stuff in Act1 with a new environment. So it's pretty standard. Now, as I said, I'm sparing you the details. The full semantics was 75 pages of lovely handwritten equations. I was ever so proud of them. I then did another 9 additional reports because there's lots of additional ASN1 features, subtypes, functions, etc., etc. So that was the main report and 9 additional reports. So what did I learn? Well, what I did was fiercely faithful to ASN1 and all its peculiarities. If you have ever touched ASN1, boy, is it peculiar. But for me, it was actually the most satisfying thing I ever did, sort of, not the most, but very at that time, satisfying because I wrote my own denotational semantics and it wasn't like a standard programming language. And it's actually so powerful to do that yourself. It was for anybody else, incredibly boring. Those 75 pages, I defy you to read them. Really terrible. And when I presented it at a conference, someone from industry stood up and said, we preferred it when everything was informal, and we could implement ASN1 any way we like. This is a direct quote. So, unfortunately, these 75 pages and all those additions made absolutely no impact at BT whatsoever, despite them paying for it. So I got a wee bit depressed, and it was actually between Christmas and New Year, I think of 1990, I decided I was going to implement this as an interpreter in Miranda. And I remember sitting at my kitchen table, just getting so angry. It was so much fun. So I implemented the 75 pages, and you know what I found? I can't believe it. Mistakes. Many mistakes in there. But it came to life, and then I gave the interpreter to BT, and guess what happened? All sorts of stuff happened because they started to use it. And it just absolutely changed my life, and I learned, you ever make a model, you ever do any mathematics, make it come alive. Take it out for a walk, give it some exercise. You've got to show what it actually does, because it's too easy to write a black symbol on a white page and think that's it, that you've solved it. That A, someone's going to read it, and B, that it means what you want it to do. So that's my very first lesson, and I've carried that out throughout the rest of my life. So every model I've developed ever since, I have taken it out for a walk in one way or another. So, okay, roll on about 10 years. Through a chance meeting, as they happen in a pub, I met a leading cancer researcher. Through him, I met some cardiovascular researchers, and I fell into a whole new area of what's called biochemical signaling. And I'm going to talk about a particular application in intracellular pathways. And this, loosely speaking, is a signaling molecule comes in and meets a receptor at a cell membrane, and then it sends a signal into the nucleus which affects a change. And often, cancer is the result of the path by which it goes from the membrane to the nucleus is either changed or speeded up or slowed down. So the question is, why to model this is because we want to understand the interactions and the sensitivities, to study the effects of interventions, to study the effects of faults and degradations, and to test hypotheses. Basically, we generally want to look at when things are not functioning as they normally should. Here is the schematic that the medic gave me right at the beginning. So you can see, this is where I need to put, you see the cell membrane and you see the nucleus. And a molecule comes hits the receptor, and it can go into the nucleus via different paths. So I'm going to tell you my key observations. The one I didn't write down here because it's quite rude is, first of all, these medics and biologists use symbols quite willy-nilly. I found out, like, why have you used an oval there? Oh, because I wanted to, not because it's standard to use an oval for this type of protein. Anyway, and they just never got it. Anyway. But the key for me is these are processes. So as he's describing what he's doing, I'm saying these are processes. Moreover, they're not independent processes, they're processes that are communicating with each other. And how are they communicating? It's through phosphorylation. Do you remember ATP and ADP? School by adenosine triphosphate diphosphate. I remember my teacher telling me ATP, the building block of life. Well, that's what is used for phosphorylation. So phosphorylation is the attachment of phosphoryl group to a molecule. And in effect here, it's to switch it on or switch it off when it's dephosphorylated. But what's quite important here, these are not only communicating processes, these are processes in which reactions occur, and rates at which things happen are very important. So, techniques. The models that I developed here are CTMCs, continuous time Markov chains. I hope you all remember those. How I describe them is using process algebra, though, using stochastic process algebra, and also using PRISM, the fantastic probabilistic model checker using reactive modules. And the properties, so this is now, by the way, going to be a recurring thing. Instead of an interpreter, I'm going to use logics to reason about a model. So here it's the temporal logic CSL, continuous stochastic logic. Now, what's different about what I did, because you think you're alone in the world doing this, and then you find, like Luca Cardelli's looking at molecular processes as well. You know, suddenly half the world's doing this. But the different thing that I did was look at molar concentrations. So I don't look at molecules, I look at molar concentrations. So if you're into epidemiology, this is like looking at populations rather than individuals. I also tried to develop plug-and-play processes so I could assemble different types of networks. And in intracellular signaling, where this reaction occurs also matters, not only with what other process it's communicating, but where. And there's these things called scaffolds. So you have to think about, is this reaction occurring on a scaffold or not? So I'm going to give you a very simple example which doesn't have scaffolds and doesn't have networks, but it's one simple bit of the MAP kinase pathway. So MAP kinase is a simple way of calling the RAF-MEK-ERK pathway. MAP is mitogen-activated protein kinase, I think. Anyway, so the idea is, they use asterisk to denote phosphorylation sometimes. Sometimes it's hash dash PP. God knows why. Anyway, so RAF, phosphorylated RAF, can phosphorylate MEK, which phosphorylates ERK. So there we go as the schematic. And the question I was asked, what's the impact of RKIP, which is the RAF kinase inhibitor protein, on that pathway? The very, very simple bit of pathway. Here is the schematic that I was originally given for this is a bit of the MAP kinase pathway. You see RKIP down there at the bottom, slightly to the right. RKIP, there's RKIP dash P, which means it's phosphorylated. You got that? Okay, so, sorry, something's happening interesting here. Lost my ear. Okay, so here we go. The circles are proteins. The squares denote reaction rates, whether they're forward, backward reactions or just dissociations, which are products. And the numbers, well, the K11, K12, blah, 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 in the boxes are the rate coefficients. These all come from mass action kinetics. So I look at this. Oh, and by the way, we have a photo. This is all from experimental results from Walter Koch. If you ever meet him, he's an outstanding cancer researcher now in Ireland, and he always gets embarrassed when I put up a photo of him, so don't tell him that you saw a photo of him. Anyway, the first idea was that each of these proteins is a process. Oh, so, oops, what are the questions? Sensitivities, can we detect, classify, crosstalk, look at scaffolds? So I'm going to look at a model, and I'm going to give you a bit of a process algebraic model. And this model is based on the idea that a protein, a molar concentration, there's either some or none. It's high or low, right? So there's just two. Now, I can crank this up to any number of levels, but let's just start easy. High or low. So when RAF1 is high, what can it do? On that schematic, look at the outgoing edges. So it can go into a K1, K2 reaction, or a K12 or K13. Do you see? It can go either way. So I express that algebraically using prefix. Phosphorylated activated RAF1 can do a K1 reaction and then behave like RAF low, or that's the plus operator, or it can do K12 and then become low. You got that? We can then say, what if it's low? Then it's like, let's see the incoming arc. So it can do the opposite of those two. It can do K2 and the K13 reaction, but it can also do the K14 product and the K5 you see from the yellow squares. Got that? Great. Right, that was one. So I do that for the whole thing. So that's one way. Oh, I think my ears come off again. Right. If I was Dr. Spock, I would not have, Mr. Spock, I would not have this problem, would I? Okay, another way to look at this is to say, instead of these are individual processes, this is a collection of pathways. So I could say there are sub-pathways. Remember, this is my original whole pathway. Here's a sub-pathway. You could say there's pathway 10 and pathway 11, originating at both those two proteins. And you can see, this is where I really want to, pathway 10, from down at the bottom, starts and says it can do a K9 reaction and then become pathway 11, or pathway 11 can do either a K11 or a K10, and then follow and become a pathway 10. Right, I do that for the whole thing. So I have two ways of looking at this. In the first one, I have 13 proteins, and so 26 equations for high and low. Or from the pathway view, you have to believe me, there were 5 pathways in that. So I have two completely different views of looking at this network, and guess what? They're bisimilar. They are both denoting the same underlying CTMC. So you can do lots of theory about showing the equivalence of those. You want to take either one to prove different properties. Now, in terms of properties, one of the questions has to do about sensitivity. So what's the effect of the binding of RKIP to RAF1 on ERK-PP? So that basically says, does RKIP dampen down or amplify this pathway? And this graph, if you can actually see it, shows you the effect of increasing the rate of a reaction on the production of output. So what this shows you is, yes, RKIP is dampening down this pathway, and that might be something that we want to do. So what you typically want to do is, so RKIP is something you want to introduce into this pathway. Okay, there are other things you can do with multiple pathways. You can detect how they interact with each other. You can categorize them, for example, using logic properties. I said this was by cartoon, but so there's some CSL. Is substrate always available? Is it possible to activate a pathway without activating another one? So you can say whether yes or no comes from that. So I got to speed up here. What did I learn from doing this? Reactions are processes. Individuals versus populations. This is not something I had thought about in computer science before. Typically we have, 3 machines and 1 router, or 100. We don't typically talk about populations. So it's about representing quantities. I hadn't worked with CTMC models before. What I discovered, well, actually it was my PhD student who discovered it. Vlad Vyshemersky said one day, when we were doing increasing the number of levels, he says, this is Euler's method. It blew me down. It's absolutely Euler's method. So we can show in the limit, these are exactly ODEs. So you don't need ODEs anymore. I could also develop propositions for looking at quantitative trends, which I have no time to tell you about. But the whole thing was, for me, it was a lovely journey back into science and also to reflect upon science and engineering, the difference between modeling something that is and engineering, which is developing something that we want. And in a sense, the two have come together. We're modeling things that are occurring in nature, but we want to change their behavior. Okay, time to move on again. Number 3, roll on, this is about 5 years. Back to computer science, looking at home network management. So this is the idea that a PhD in computer science doesn't enable you to set up your own home network, certainly never enabled me. So I was working in a project, can we help home network managers, and also can we introduce policies that they can invoke on their home network. So here's the idea, you've got a home network, laptop router, and the visitor comes to visit and they come into your, in the range of your router, the question is, did they join, does it work? So did the iPhone join? Did the router assign the right address? Did the firewall stop any traffic, etc.? And if you had any policies are they working properly? So now this time the technique was to develop online models. Why did I want online models? Is to check about the state of the system, diagnose problems, and check that the policies are being complied with. So here's a description of the scenario. On the left is you've got network traffic happening, you've got network events, and you've got policy events, so you can invoke a policy. And these are both captured in a stream database as events, which is then used to update a model. So in effect, we're keeping a model that is a reflection of the state of the system over there, and then performing analysis on that model, and all of that's on a router. Now, you may be saying, digital twin. This was 2011, before the word had been coined, right? They've been around for a long time, so this is about online models. And then we can also send feedback from this analysis to the network and also to the policy person. So this time, the models, so I'm modeling events and control policies, and I use Bigraphs with sharing. I'm saying I must say we. Really key person is Michaela Sevignani that I developed this with. So Bigraphs was a process algebra for time and space developed by Robin Milner. We added Bigraphs with sharing. So fundamentally, in Bigraphs, the underlying structures are trees. We changed it into graphs so that you can actually have overlapping topologies, which you'll see in a minute. Why is this relevant here? Well, first of all, you should all be using it because it's great. But the point is, unlike most process algebras, the rules are not predefined. The operators and rules and entities are not predefined. They're all rewrite rules. There's both an algebraic and a graphical form, and I'm going to do everything in the graphical form, but trust me, they all translate into the underlying algebraic. So it's going to look like a cartoon, but it isn't really. So what's analysis? We want to compliance with a policy, and this just means matching on a bigraph. And you just want to check that every model update. So on the left is a real drawing, very simple, a machine and a router, and each have got a signal, right? They've got a signal and they overlap. This is why we needed real underlying graphs and not trees. On the right is a bigraph representation of this. In bigraph graphical notation, you can use any shape to denote an entity. You can also use colors. So basically, you have a very, very rich type structure. There are no colors here, but the next example, there will be colors. So on the right is a bigraph. Hopefully, that looks rather similar to the picture on the left. And here the idea is the router and the machine one are linked to their signals. The router can sense M1's signal, and the router and the machine are linked. They're part of the network. So I'm going through this very fast. You'll just have to trust me. So we then define rules. So here's a rule that says, how can I add a machine into a network? So on the left, I just don't want to point, on the left is a bigraph, which has got a machine, there's a router and there's a signal. There's also this black thing, which basically says, and anything else you want to substitute in there. And on the right, we have added machine M, right? So this is just a rewrite rule that says when you add a machine to a bigraph that has these properties, then you end up with this new bigraph with the machine in it. You can read that very quickly because on the right-hand side, notice that the machine and the router are in the intersection of the two signaling nodes. Okay, I can then have a rule to remove machines. So on the left says I've got a machine, I've got a whole lot of other guff, at least fulfills its constraints, and I end up with no machine afterwards. So I can then apply rules like this. So here's a scenario with two machines. So that's a scenario I want to update the model, and I want to remove a machine. So there's a picture up top, and down the bottom is the bigraphical representation of that. So on the left is the rule, on the right is the application of the rule. And you see those two red ovals? I have no idea where they came from, and they are a mistake, right? So moving on, I then want to check network properties. So I use that by predicates can just be encoded by other bigraphs. And so if they match, the bigraph fulfills that property. So I use that for policies which can either allow or forbid things, and policies can be enforced, dropped, or checked. What I want to show you is that we do this in real time. Oh, no, I wasn't showing you that yet. Remember the old days when you wrote things on OHPs and you could see everything you were about to talk about before it appeared? Yeah, anyway, those were the good days. Anyway, here's about invoking a policy that blocks all incoming traffic from a remote host. Anyway, what I did want to show you is we could run that whole model, update it in real time on the router and do checking, and there you can see, I hope you're impressed by the time over there on the left. So this is about the number of machines and networks, so the average time. So moving on, novelty, what did I learn? Online models, well before digital twins. Bigraphs with sharing and overlapping spaces. Michaela has developed this wonderful tool called Bigraph ER, written in OCaml. It's lovely, so it does all of this for you. No need for temporal logics, I only needed state predicates. State predicates are just bigraph matching, which is just subgraph isomorphism, which we actually encoded up using a SAT solver. Lots of policies interfere with each other, and many in unanticipated ways. And that's going to be something we will observe again and again. Okay, that was example 3. 2 more to go. Have I, nearly 20 minutes. So, I'm going to talk about what's called the Savannah game. This is a really interesting mixed reality system that involves location, time, sensing, and cognition. So let me try and explain this. The idea was there's a virtual savanna, i.e. a desert, jungle, physical terrains. Think real savanna with animals on it. And that's a game, and it's mapped onto a physical, like a football pitch. And there are players who are playing this game, and they are instrumented with GPS, and they have a PDA. The animals in the savannah are typically lions and impalas, and the players are the lions. And in the game, depending on where they are in the savannah, they might be near water they can drink, they might be near tall grass, which is good for hunting. They can see nearby animals and they can kill them. So, by the way, I was not involved in the development of this game. I tell you, by the way, this is just before Pokemon Go. I think this is much, much more sophisticated than Pokemon Go. This is really, really cool. But they can attack, drink, etc. when possible. So you can see on the far left, there's the kids out there playing it on a real pitch. There's a display of what they see on their PDA. There's the savannah, the map of the savannah, and they're using these devices to see stuff. Now, there's an additional twist, the cognitive bit, the social bit. They can only kill, they have to kill in groups, so they have to form. So players have to, in the real social world, agree to hunt down an animal in the savannah. You got that? Good. Now, I was brought in. After they developed this game, they'd implemented, and they did a whole load of user trials. Those photographs are from real user trials. And there were some problems. And there was this thing they called the 3 girls, a boy, and an impala problem. And when you got a problem like that, what do? You call in your modeler and say, Muffy and Michaela, what on earth is going on here? So our task was to figure out why was there cognitive dissonance? Why were these players suddenly very confused about where they were in the world? And what was wrong with the design? So we used bigraphs to model, because this is spatio and temporal evolution. We used bigraphs predicates for reasoning. We used the graphical notation to its fullest to try and communicate to the designers and to us. And a very key observation right from the beginning is to say there are 4 design perspectives for this game. And here they are. So, which way? Starting off, we have the humans over there on the left, the human players. Down at the bottom is the computational world, what's happening in the software. Then we have the technology, the sensors. And then up top, we have the real physical. Remember, they're doing this in the physical world. So a key thing that I learned right from the beginning, this was us deciding there are 4 perspectives, and we should look at modeling those 4 perspectives and then try and fit them together. Now I'm going to give you an overview of the bigraph model. These are real bigraphs here. They're pictures that we drew. These are the graphical notations, and also using colors. So let's go around them. I'm going to start off in the computational world, down at the bottom. I have things like the lions and impalas, and the notion of a locale, where they are. Remember, this is in the computational world, and the rules are about eating, eating lions, but also the lions, the lions eat and drink, and they go hunting. So that's where I'll spare you all the rules for those. Oh, do I go back? You'll see there's a bigraph rule. It's a bidirectional rule. And basically on the left, there's a lion and an impala who are just coexisting in a locale. On the right, they've turned yellow because that means the lion's seen the impala and is in a sense holding it. So we use the colors to denote change in types as well. The physical world is the players on the field, and this is where we pair the players or the children with the lions, and they can initiate attacks. And their color changes to denote whether they're attacking or not. The technology is about GPS position, so this is where we actually have real XY coordinates on a Cartesian plane. And so you can see we can go from rules where there's nothing to something's in an area. So keyword is area there. So the rules are entering game, moving around, dying. And then finally over there on the left is human. So what can the humans do? Here we decided we need to model some notion of social interaction. So this is where I read up about the theory of proxemics. Hadn't heard the word before, now I know all about it. It's basically, are you in the proximity of another person so you can have a social interaction? An easy way to think about this is you could see someone, but it's not necessarily that. It might be you're within audio range. You're in some way in some social thing-me, and the thing-me's are called auras. So you're within, and auras can be, so there's some pictures of auras. You have embedded auras, you have overlapping auras. You got that? So that's all about personal space. So that's just a summary. Let's move on to the 3 girls, a boy, and an impala problem. What I'm going to do is we took an execution trace. Well, we looked at the video, and and the log, and we could construct an execution trace and show what that execution looked like in our bigraph model. So here, what I'm going to show you is always got the same format. On the left, I'm combining the human and physical to make it a bit easier perspective. In the middle, I've got the computational perspective, and on the right is technology. And we start off with 3 girls. They actually have real names, but I thought I shouldn't reveal them. We're going to call them X, Y, and Z here. And they're all in a shared aura, which means they're kind of, they're talking with each other. Okay, X, Y, and Z, there's their names. Now, X is in a locale marked to area A up top. You see that? And there's also an impala in that locale. So that's in the middle, you see the impala. Y and Z are in the lower locale that maps to area A dashed. Got that? Great. So aura, locale, area. In the next state, Y enters the same locale as X, so moves up into the locale with the impala all in area A, right? Z then enters the same locale. So now you can see, this. I so wish I could point there. So now you see the three girls are linked to lions that are all in the same locale with the impala, and they're all in the same physical GPS location, GPS-ish location. Great. That was state, we're only in state 2. I think there's 10, don't worry. Anyway, state 3, Y's GPS drifts out of locale. This is real world. So, Y is no longer in that locale. State 4, the excitement, the boy enters the locale. Did you notice, I showed you photographs at the beginning, there were 3 girls. Did you notice there was a boy over there? The boy has entered the locale, and you'll see his lion up there, up top. And he's in the area, but he's not in the aura. He is not in the girl's aura. But there he is. His lion is in the locale. The boy sees the impala, right, clocks it, so they go yellow, and he initiates. But remember, it requires a group of 3. X now joins the group. She mistakenly thinks she has initiated the kill. So she thinks she's yellow with the impala, but she's actually blue and red with the impala. Z then joins the group. So now there are 3 children in the attack group, but they're not all girls. It's 2 girls and a boy. You got that? So what does that mean? Sorry, but they've just killed the impala, right? So the impala has gone. The boy leaves the locale. He walks away. But Y, down there at the bottom, is hungry because she didn't get to eat any of the impala. She sees this in her, right? And she doesn't understand why the others have eaten, but she doesn't understand why she was not in the kill group, because she actually never knew that she drifted out. But the problem comes from state 4, where X and Z are in the same locale, but they're not in the same aura. And the girls are not aware of the presence of the boy in the locale. He's in the locale, but not in the aura. You got that? So how did we uncover this? Is we looked at the model and we started taking perspectives pair by pair and looking at properties that would be desirable in a well-designed system. And one property would be that if 2 children are in different auras, then they should be in different areas. Not that if you're in the same, so if you're in distinct, you should be in distinct. And actually we found that, so we can do that all within bigraph matching, and we found that that was not true. So, end of that. What did I learn? Bigraphs are really powerful notation for communication with designers, because the designers could follow that execution and understand what had gone wrong. They had not twigged that they were missing this connection between auras and areas. The 4 perspectives were really important. The level of abstraction, of course, is key, and to work at the right level of proxemics was really important. Notice we didn't do anything about intention, right? I never try to model what a person thinks, or all you can do is observe. All you can do is observe. But the really novel thing here is this is modeling for the analysis of replay for a behavior that actually happened. This isn't about design. This is about understanding something that actually happened. And on that theme of understanding something that actually happened, it's now time to, you'll be relieved, I'm moving to number 5. 5 out of 5. Okay, so finally, I'm looking at user interaction styles. The reason I picked this one as the 5th one is, well, I like it. But second, of course, it's got inferred models. There has to be some AI in this talk somewhere, doesn't it? Because it just wouldn't be anyway. So there's some unsupervised machine learning here. So the question was, how do users actually interact with an app? and can we redesign it to suit their styles? Put more generally, is you may design a system for use however you like, but when users come to use it, they may use it in a totally different way. Obviously, they can't do something you didn't design in, but the load, the stochastic, the way in which they explore states, and the order, they may do that in ways you never anticipated, and therefore they may not be exploiting the properties that you have, or you may, in our case, we were looking, are there things that we should better design for because the way people actually want to use something. So the techniques and models, the key here is to log interactions. So this is experimental work. We log interactions with a system. So those are state, oops, I said the word state, sorry. These are changes of internal thingy, yeah. We're going to, but not only do you get all those log files, we then segment them. So we wanted to look at usage over, 1 day, 1 week, 1 month. Is it the 6th month? Is it the 1st month, etc. We then inferred models that happen to be autoregressive hierarchical Markov models. These are, in our case, admixture models. I'll come back to that. And then we analyze the model with temporal logic properties, which then allows us to deduce something about the behavior that's being encapsulated. So, as I said, I'm doing this by cartoon. So here's some cartoons. User traces. For each user that's been using a system, we're recording all the underlying state changes. So let's just represent states by different colors. So this is a pretty simple system. We only have about 4 colors. But anyway, user 1 moves from yellow to red to blue to blah, 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 over time. So this is a time series. So we have time series for every user. And then for all those time series, I can then segment them into days. And from those, we deduce, no, actually we infer a discrete time Markov chain, which denotes the probabilities to change state over those traces. Except it's not just one. What we're looking for, what's called admixture. Anyone heard of admixture? Mixture models, machine learning? Yeah. So the way it was told to me it comes from like crop breeding or animal breeding. If you breed a black dog and a white dog, you get some black puppies and some white puppies. That's a mixture model. An admixture, then you get some Dalmatians. You also get some things that are black and white. And you got the idea. Right, so not only do we infer one discrete time Markov chain, well, I can infer as many as I ask. So in this case, I can infer 2 different activity patterns. So, and you could think of this as a style. In one style, I have probabilities to move between these states. In another style, I have a different set of probabilities to move between the states. And you could ask, well, why would you have different styles? Well, think about it. Where you use an app, your usage style might depend on whether you've used the app recently or not, whether you're tired or fed up, whether you just want to explore the app, you're really focused and you know exactly what you want to do. You're on a train and using the app is difficult to use in a different. There's a whole lot, we haven't a clue. All I know is we can observe different different styles. So, just going through it, it's the probabilities of transition that change, and then I can move in between these 2 DTMCs. If you're interested, this is using EM estimation Baum-Welsh. If you're not, then just skip over that. Then I use temporal logic, PCTL star, temporal logic properties to reason about either the behavior within an activity pattern, for example, the probability to visit a state, or properties over patterns. What's the probability to move from a state in one pattern to a state in another pattern? There's this CTL star for that. Unfortunately, I don't have time to go through that, but trust me, it works. Okay, so very quickly, a case study. Again, I didn't develop the underlying app, but then I worked with the developers. So there's this thing called App Tracker. Now, it all gets a bit meta because App Tracker is an app to track your use of apps. You got that? And then we did analysis to track you get it. Anyway, so this is all instrumented. It's had over 35,000 downloads. So this is not a trivial experiment. This is real stuff in the wild. So we took user logs from these downloads. There's just some more display. So, idea. The underlying state space, there are 16 high-level states. That's all you need to know. What you need, that's not an activity pattern. Here's some activity patterns. For example, here's 3. If I set this parameter called k, saying how many activity patterns do I want? Or in Baum-Welch, how many clusters? This is clustering, by the way. How many clusters do I want? If I want 3 clusters, here's 3 example clusters from this from these logs. But remember, it depends what time period. There's so many dimensions here. What time period am I taking them? For example, even looking at number 2, from the first month to the second month to the third month might be really quite different. You can see there's quite different probabilities. By the way, I'm using thick lines to denote higher probabilities. So all these have this is all really quantitative underneath there. I then I say it's we, me, and Oana Andre, remember her name. We then did probabilistic model checking with all these properties on all of these models over all these different time segments. Fortunately, I can't show the details, but what you will see is, more or less, it's very easy to classify the 2 patterns we got when said k was 2. You'll see they come up with really similar results. So the properties may be to deliver a probability or maybe to deliver an actual integer. We then classified the patterns depending on the probabilities, the states that were involved, and the length of sessions. So we actually know the time someone was engaged with the app, and actually that affects usage style as well. You combine all that with k equals 2. In this thing, there's 6 possible combinations. Only 4 were observed. Here's the 4. I've used names to give you an idea of what they're denoting, but these aren't just labels. So you'll see it's glancing, specific, and browsing summary for the first day, week, and month, and then it's different patterns in the second month and third month. So loosely speaking, you can say there are different activity patterns in the early days compared to the experienced. That's just saying what the activity patterns are. Now then, we're interested in, do people move in between them? And here you can see, for just k equals 2, which is a very simple case, the probability to change activity patterns from the first day into the third month. You see, it's very likely. So again, fat arrows denote high probability, thin arrows, dashed means very, very unlikely. So you can see there's a high probability to change in the first day, in the first week, but not in the third month. So summarizing, you see browsing in the early days, focusing and glancing. So we redesigned the app to support focusing and glancing. So there's a summary of what we did is we split up and moved stuff in the top, and then we came up with App Tracker 2, which had a different state space. So I will spare you all the details. So App Tracker 2 then went out into the wild. All those, well, it wasn't 35,000, I think it was 22,000 downloads. They all used it. We took all the things. We did all the inferences. We divided it all up. We did all this stuff. And what do we end up with? That in App Tracker 2, you will see the probability to move between activity patterns was extremely low. And my interpretation of that is we have designed now the system that suits user styles, because when they find their style, they don't move between them, whereas in the first one they did. So, just a few words about sensitivities and the validity of everything we just did there. It all depends on what are your observable states, how you segmented the data set, the time series, the number of activity patterns, K. One could ask, is there an optimal K? Well, K can be as big as you want. You ask for more clusters, you'll get them. It very much depends on the individual software. Never seen one yet where k greater than 7 gives you anything useful. K equals 4 is usually pretty good. Depends on the inference, it depends on the states. Now, we had to use jailbroken devices, which also means we're getting a very biased population here. People who use jailbroken devices are, people like you, Simon, They are typically young men in black t-shirts. And a real problem we had was, because we did this through Apple Store, you couldn't link, when we released the new, we couldn't link the new with the old. And so that really annoys me. So we don't know how many of the second users were first users. So that's about doing modeling in the wild, really quite hard. So what did we learn? This is about modeling actual behaviors, not what the system's designed to do, but what people actually did with it. What computational pathways did they take through the app? It's using unsupervised learning. I have been pretty against machine learning before this, and actually it was a delight to find a truly meaningful application. Real-world deployments, there are lots of biases. There was an inbuilt bias here because the way we had to release the software. What annoys me a bit of where we tried to we published much of this in the beginning, but no one seemed to be interested. They always seemed to be interested in experiments with 10 student users. We were using real people out there in the wild, and I feel that we were poorly understood about all the trials of that. And when we were the full paper, which shows AppTracker 2 and developed, we've actually never published it. It's on archive. TOSUM didn't want to take it because they didn't like our experimental design, that we hadn't added various things to have textual annotations from the users. Well, you can't do that when you've got 22,000 users, and this is an experiment over 6 years. So experimental design is really important because if your reviewers don't like it, you can't do anything. Anyway, I'm not bitter or twisted at all. Anyway, what I also learned when we went into this, we thought there was one data set. We really had not realized how important it was to segment your data sets. Experiments take a long time, so think carefully about design. Temporal logic's useful again and again. And this was a really new, novel application of modeling to inform redesign. So not to inform the original design, but to inform redesign. So you'll be pleased to know I'm about to conclude. I'll just summarize. What did I just do? Looked at 5 examples. Protocol languages, what were the key things? It was about a denotational semantics and interpreter. The signaling in biochemistry, it was about process algebra, CTMCs, and using the logic CSL. The homework, sorry, that was the name of the project, domestic network. That was using Bigraphs and predicates as an invariance, and it was about online modeling. The 4th was a mixed reality system. Bigraphs again, the key thing was design perspectives. And again, using invariance, didn't need full temporal logic. The 5th was using much more complicated than DTMCs or CTMCs, this whole layer, these autoregressive higher order Markov models with underlying DTMCs. And the whole thing was these were inferred from actual data. And the last one is actually, the last 2 actually involved humans. Prior to that, I had been steadfast, I was never going to touch anything involving a pesky user, but I started learning. It's quite interesting modeling what you can observe about users. There's a whole lot of other models I don't have time to tell you about. Recently, I've done a lot of stuff on BDI agents, protocols galore over the years, medical devices, service failures, and I once did a most ridiculous thing. I did a stochastic model of War and Peace, which is kind of for fun, but you can look at if the rate of Napoleon's advance on Moscow had been different, what was the likelihood, or the probability actually, of Pierre marrying Helene. Anyway, just ridiculous, but interesting fun. So recurring theme, theory is always challenged by applications. If I hadn't done these applications, I would have never advanced my own bits of theory, for example, in Bigraphs. You've got to use theory. Over the years, the automated reasoning tools has just become so much better, and there's so many more of them. It's something I've totally skipped over, is how to use automated reasoning. I have become increasingly stochastic, probabilistic, much more online modeling, more interested in human in the system, and very much for replay of behaviors in the wild. That's probably much more what I look at these days, is actual behaviors. Interactions and interworking problems are absolutely everywhere, from pathways to policies to usage styles to perspectives. So, this might be my last slide, or maybe not, you never know. It's coming very soon. The future. Okay, my message is models are for much more than design. Very much I think the future is online decision support. I'm much more interested in modeling something that is, rather than something that we would like. Data, I've always been again data. I like processes. Data for me has always just been so boring. You know, it's just a static snapshot of a process. But I learned, particularly through these logged interactions, data is actually something and really rather useful. And models of processes can be informed by data. The whole ecosystem of what you do with models is really important. Don't have time to talk about that here. But the final thing I want to say is something that I think I always knew, and I imagine you always knew. The really key thing is not the model, but it's the modeling process, is the exercise of going through that. Don't worry, I'm now on my last slide. I don't have time to say all their names, but all this work has been with my collaborators, and I want you to know their names. There they are, and I want to thank them very much. And that's me. Thank you.